right?
Hello. Thank you very much for the introduction. So, as you heard, my name is Marko, and this is my colleague Enes. And today we will talk a little bit about challenges and pitfalls of modern computer vision models. So, we are coming from data science team from Styria Group. If you haven't heard about Styria, it's the biggest regional and biggest Croatian media company. So if you are from the region, then you probably heard of 24 Sata, Večernji list, Njuškalo, Poslovni dnevnik, and these are all Styria brands. So today we will talk about, for start, just briefly about the evolution of computer vision models, how these models evolved from handcrafted features to powerful deep learning models. This is important to understand the problems that my colleague will demonstrate later. Just briefly about high dependency on the training set distribution of these models, with some practical examples of specific classifiers, and then we will speak a little bit about self-driving cars as an attractive use case in this field. And after that, my colleague Enes will demonstrate some adversarial attacks on deep learning models. We even made some small demo project just for this lecture. And he will also present some strategies for defending against this kind of attacks. So for start, regarding the evolution of computer vision models in general, we had big breakthroughs, and I would even say revolution back 5 years ago, somewhere around 2011-2012, with the emergence of new technologies, convolutional neural networks. And the reason for this is twofold. The first is that we got our hands on the big amounts of data, so big data sets, most notably ImageNet data set that is used for the most scientific research, and also the evolvement of the hardware. So before that, we had handcrafted features like the ones on the image. So here we can see some edge detectors and some sift features detected on the object, but as you can see, if we slightly move the object around, we lose some features and get some other ones recognized, and these features are really unstable, and shallow machine learning models placed on top of this just didn't work quite well. So with the emergence of powerful hardware and lots of data, we got resurrection of neural network models, most notably CNNs, which are trying to mimic the way how the visual cortex of mammals work. So these networks have two-dimensional layers, which we call convolutional filters, placed in a series of layers. And with each layer, the network uses more and more abstract features. So for the image on the input, first layers detect primitive and less complex features, and the next layers detect more and more complicated and abstract features. And at the end, we have this standard traditional multi-layer perceptron neural network, and at the exit of the network, we have probabilities for classes presented in the training dataset. So these networks are really powerful. We say that they are really descriptive. They can really well fit the data, but at the same time, this is their drawback, because they tend to overfit the data, describe it too well. And for specific use cases, we need to have specific models trained on specific data. And this is the reason why just plugging in some third-party API won't work for your specific use case. And the next reason why this would be a bad idea is because we do not have this API under our control. So we do not know which dataset was used for training and what distribution of this dataset is, and even more important, we do not know how this model works. We even do not know sometimes this with our own models. So this is one example of a model that we trained on our own data. And when presented these images, as you can see, both images show BMW car. And when we ask our model what is this on the image, for the left image it says BMW car, but for the right image it says PlayStation video game. Why is it so, and is it good for us? Well, we trained this on our own data set, where we also had some PlayStation or computer video games as objects in the database. And this image on the right is not the real photo of a car, it's a render or a drawing. And it reminds the model probably on the Need for Speed or some similar color from the video game, and this is the exactly behavior that we want. But if we plug in some third-party API, probably for both of these images we will get result that it's a BMW car, and this is not something that we want to achieve, of course. So these problems are present in various different use cases like security and surveillance systems, fraud detection, drones, self-driving vehicles, and so on. So we will now focus a little bit on self-driving vehicles because they are so attractive now. As you can see here on the image, we have some interesting result. Getting back a few months ago, Elon Musk said that probably we will not need LiDAR systems on self-driving cars, that we can rely completely on computer vision and cameras. And why he said so? Because he realized that how powerful these models are, and the fact that humans also drive the vehicles relying only on the cars. Okay, only on the eyes. Okay, we have two eyes, and we have stereo vision, so we have also some depth. But not just the depth that is important, but also the context and the realization and prior knowledge that we have about the world around us. So here, for example, you can see person and bicycle imprinted actually on the back of the car, and the model thinks that it's bicycle or person in front of it. So it's not the behavior that we want. And this is just one example of potential problems. There are many other problems. And for some of them, my colleague Enes will now show you a few more examples.
Hello. I'm going to show you how to train a neural network that can drive a car. What you need for training any network, you need some training data, and in this case, what you need is some video footage of car driving, and for each of the frames of this video, you need information about velocity, gas, brake, and what you would do, you would create an convolutional neural network architecture, which takes as an input image or a couple of images from the video, and as an output, it returns velocity, steering angle, brake, gas, and also we can have as an output we want to recognize the objects, for example, traffic signs, pedestrians, and so on. So you can do this in one convolutional network. Optimization objective for this model would be you try to predict the values for steering angle and so on that are as close as possible to your training data from so real driving footage, or some data that was created in a self-driving cars simulator, for example, for simulating dangerous situations to enrich your data set. On the other hand, for object recognition, for example, traffic signs, what you need is to classify. You need to classify them as accurately as possible. And here we use usually a cross entropy loss function. The details are not that important. Here are some results. For example, this is a publicly available data set, and it is of German traffic signs. And as you can see, these signs are not really clear images, yet the classification accuracy is above 99%, and I have personally trained the model to do this, and it works really well. Also, you can using this method, as I've mentioned earlier, you can really train the car to drive reasonably well in a simulator. So it sounds simple enough. So now let's. Recent research has shown that these neural networks can be easily fooled. So let's say you have a classifier which needs to predict 1,000 classes, which means that you want to predict if something is an animal, a car, type of animal, for example, a toy or something like that. And then you would expect that if you put some kind of a random image, for example, like the noise above, or something like these funny structures, that the network will be unsure in its predictions. But they have actually created these examples specifically using evolutionary algorithms, and the networks were confident above 99.6% that this belongs to some class. For example, king penguin down left, starfish, baseball, which actually makes some sense, and the noise doesn't make any sense, but the network is very confident that it's still something that isn't there. The more interesting example of this is that we try to change an input image in indistinguishable way to human eye, and then this produces the image which will be totally misclassified by a trained neural network which achieves high accuracies on the normal data. So we've actually created a demo, not trained on traffic signs, but on human faces. The data set used was Faces in the Wild, which is a publicly available data set of human faces. And the model achieves more than 95% of the accuracy. Actually, on good images, this percentage would be much higher. And also, there was you could train that to go up, but I believe that you can agree that 95% is a good accuracy. Now, these four images that you can see below are the images that were not part of the Faces in the Wild dataset, and we want to create images which would be indistinguishable from these images, and the network would classify them completely wrongly. So how do you do this? You take your original model, and then you try to create another model which takes an image as an input and outputs another image. So this other image has a constraint, and when you train neural networks, this constraint means that you punish the network if it steers away from this constraint, and you reward the network if these constraints are satisfied. So the constraint was that the image is close as possible to the original image, and that the original classifier makes the mistake as large as possible. So these are the constraints. Just to explain what does it mean to have how do we measure is the image visually close? You look at the pixel values. For example, you know that images are encoded as an array of 0 to 255 And we try to reduce the mean squared error between the original image and the refined image as much as possible. So let's go into demo. Okay, so some Python code. Don't get scared. We'll load the networks, both the refined network and the original network. Now we'll try to classify the images you've seen in the previous slide and see what does our network tell us. So we have just explain for classifier, for binary classifier, if some class is above 50%, then we designate it as that class. So you can look at these numbers as probabilities, although I would not recommend so. So the first image was well classified, so it's a female. The second image is a male. The third image was classified as female, and the fourth image was classified as male. Now let's try to create an adversarial example. So the adversarial example should get misclassified by this network. So these adversarial examples were created from one network and then are put as an input to another network. So let's see the results now. So these are the refined images. And look at the predictions. Now, the Lydia is 98% male. This gentleman here is 98% female. This lady here is, again, about 98%. And this gentleman here is also misclassified. Let's look at the original images one more time. So you can see that, obviously, there's insignificant difference between these images. And we can actually calculate for the last image. I don't know if the projector can allow us to see these changes. So you see some almost random noise, and this is the difference. So it's minimal. Oh, I almost forgot. Now, you might think that these images are, that these networks are very sensitive to these modifications. To these modifications, obviously they are, but to random modifications or to modifications in general. Just to tell you something about the training process. When you train the neural network, you usually want to enlarge your data set by doing some transformations which will simulate the stuff that really happens in reality. For example, if you take this image and then you add some brightness or reduce some brightness, you can imagine that this image would be taken under different lighting conditions, and both of these images would be recognizable to us, and we would classify it correctly. So the algorithm needs to be aware of these small changes. But here I'm going to destroy the image by adding a large vertical stripe or horizontal stripe across the image, and then put it to original network and try to see what the classification is. So here's what we've done. So this is now input to our original network. Lydia is still classified as female. This gentleman is still classified as male. This lady, female, and male. So this huge transformation has not made has reduced the confidences and probably would reduce the accuracy of a model, but model is fairly robust to even such a huge change. So let's try. I can't type with one hand. Okay, let's try this one. Okay, again, as you can see, everything is as we would expect. The third image was almost classified as male, but our network defeated it. So let's continue with the presentation. Okay, how is this possible? Well, let's take two-dimensional data, and let's say that you have two classes. One are X's, and the other ones are circles. So the dashed line is the real line that's separating the classes. The full line is our model decision boundary, which was created during the training process. As you can see, that some of the data points are close to the decision boundary, and you need to. You can imagine that these are images, but just two-dimensional data. Now you can expect to make some small perturbation or small nudge in a direction of changing the class, and this would still be a point with close coordinates, so close image visually, but the class would be different. And now you might ask, okay, but you have these images that are far away from the decision boundary, but you can imagine that this is just a 2D. This is just a 2D, and images are usually 256 times 256 times 3 channels, which is about 200,000, and this is a standard input to a convolutional neural network. So in 200,000 dimensional space, there are a lot of directions where you can push your point, your data point, and cross the decision boundary, and this is how it gets misclassified. So one might think, okay, these are artificial examples. Can we do modifications in physical world and still get this problem? So the recent research was published, and what they did is found which areas of the image could be altered by putting some stickers or something, some small modifications, which would resemble something that you can find in reality. And if this could confuse the network to misclassify. And they actually found that these examples are fairly robust to for example, rotations of this sign, and these are real images. And the stop sign is misclassified as speed limit 45, which you don't want. So getting back to a self-driving car example. So how do we defend against these attacks? So there's no universal defense, but here are some examples. For example, we can enrich our train data with adversarial examples, and then our models will become more robust to these examples. Unfortunately, this has some drawbacks, and this is that although your network is now more robust to specific methods, you still get you can still train the adversarial network it will just take longer. Or you can take a totally different approach in training these adversarial examples, and then you would fool the network anyway. You're still operating in very high dimensional space where there are a lot of ways in which you can jitter the data and still get the adversarial examples. One other way is to hide the gradients. What does this mean? Well, our networks, as you've seen, output probabilities, so confidences. They output confidences, and if you change the image a bit, for example, you change one pixel, then you will see that the confidence also changes. It will not change in any significant way for some random change. But if you use this information, how the change occurred, then you can take the gradient, you can take the direction of biggest change in negative direction, which will reduce the confidence as much as possible. Do this enough times, and you will get the adversarial examples. So why not only return the classes? Why not our previously trained model? Why not say this is a stop sign, this is a woman, this is a man? So we could do that, and then we wouldn't have a gradient which we could use. So the neural networks are trained in a way that you take many little steps in the direction which maximizes or minimizes your loss function. You can still fool these networks. So this is not enough because it has been shown that adversarial examples are can be transferred across different architectures. So these examples can be used on other networks, and they would still be fooled. Not always, not perhaps as perfect as in example which you were attacking against, but you can do it. And so you can train a substitute network to do some job, and then you can train an adversarial network for this substitute network where you have the gradients, and then you can use these adversarial examples on your on network you want to attack. So defensive distillation. So this is another technique. You can train another classifier. You have your original model. Then you can train another model which doesn't predict the classes, but which predicts the probabilities of your network which is trained on some task. This results in a smoother decision boundary. But what this means is that the gradients will have smaller, the changes in the input data will make smaller changes to the output of the network. So the gradients are smaller, and then you need much more time to train an adversarial model to use these gradients. Okay. But there are also drawbacks. You can reduce the accuracy of the original model. That's one. And the other one is that attacker, again, can just use more resources. And there's also something that's not here, and that's that we've recently started using optimization methods which are highly adaptive. So if they come to an optimization landscape which is fairly flat, then the learning rate of an algorithm is boosted by a number or two number of orders of magnitudes, and so this landscape can be you can go away from this landscape in a small number of steps, so you can still train the network. Okay, so some few examples. I don't have much time. So you can create adversarial networks for example, avoiding spam filters, for making illegal content legal, for design a web page which will artificially increase the ranking, fooling authentication systems, and so on. So back to Marko.
So just to recap what we just said. So we gave a brief overview of how these models evolved at all. We described how they depend heavily on the training set distribution, which then translate to all these problems that we heard later. We took a look at the self-driving cars as an attractive example of this, and we show some practical examples of adversarial attacks for face detection, gender recognition, actually. Then just briefly we talked about defense strategies, how to defend yourself against these attacks. So hopefully this was an interesting lecture for you, and hopefully we put some stress on importance of this topic, because these models are becoming more and more popular, and people tend to use them, just take them for granted and just plug them in to their dataset and their use case. But it's not just as simple as that. It should be done with more cautious. These are some of our team members. This is not photoshopped. You can find us here in the conference and ask some questions. And of course, if we have some time, I think we have for a few questions now, we will be happy to answer. Thank you.
Thank you.
Okay, no questions.
Okay.
The next topic is Malio teaching a machine to detect malware. The presenter is Toni Gržinic. About Malio. Malio is a machine learning framework that successfully detects new malware samples. Despite the fact that malware is constantly changing and non-stationary malware distribution presents a challenge for statistical methods due to the phenomenon of concept drift, Malio helps to overcome these problems and can help to better detect new malware samples at large scale. About Toni. Toni is helping organizations to become more secure, working as an information security consultant in Diverto. Besides that, he managed to write his doctorate thesis. Also, Toni will performing music at the after party.
So the talk will be short. I will not take any questions because we have to prepare the after party. So I'm Toni, and I will be talking about Malio. Malio is a machine learning framework to detect malware. It basically detects only portable, executable malware. This is my agenda. This morning I didn't have any slide. I built all slides when I was listening to the politicians. So the talk is not prepared, so stand up and enjoy. Back to 2014, I was trying to write my PhD thesis and find a topic. Basically, I was trying to detect anomalies in time series. I was analyzing logs, and I have a big problem. RDD, I was working at Carnet, and basically I had a lot of data. It was cool, and I was doing math, which I love, but I have one big problem. The biggest curse of big data is when you don't have enough data. The Carnet NOC, the Network Operations Center, was on summer holidays. I didn't have any data. The annotation of the dataset was painful. I was waiting for the attackers to attack our network, to annotate the dataset, and to learn my models. So I have so much problems. So I was talking to Tonimir. Tonimir is my mentor on the PhD thesis. And he said to me, I don't know, it's your problem. Be creative. So I changed the idea. At that time, Game Over Zeus botnet was disrupted. So I said, okay, that's a big thing. Let's see what we can do here. I was listening to the Endgame talk about binary pig. Binary pig is a Hadoop framework to extract data from from portable executable files. And I said, that sounds so interesting. And it's better than the anomaly detection thing because it doesn't have so much math, it's easier, and it's more sellable. So what problem I'm trying to solve here? So the problem with antivirus is the number of signatures. The antivirus companies cannot stand the competition with the malware authors because they're so creative. It's basically a catch-up game. So every year, the number of signatures goes up. It goes up exponentially. This is basically a picture for the Romanian CERT about the evolution of ransomware. So you can see it's so much samples, new things and stuff. But who is Malio? Who is Malio is basically, Malio is my grandpa. What is Malio? Malio is a framework, I said that earlier. Uses a bunch of classifiers to detect malware. So it uses the static analysis classifier, thanks to Eero Carrera and his amazing work, and the dynamic analysis, which is based on Cuckoo Sandbox. So I take different classifiers and I fusion it together. So basically, every type of analysis has some type of problem. Static analysis is bad for packed files, and dynamic analysis is bad for anti-debug and anti-VM methods. So when I try to combine them together, I get a better result. Basically, the data problem was solved pretty easy. Thanks to the guy from Twitter. Malekal is great. It has many samples, and VirusShare is also pretty great. It has, I don't know, 100 terabytes of malware samples. Basically, this is my workflow of my framework. Basically, it used Cuckoo. It launched the malware file in the virtual machines. It stored the analysis result in MongoDB. The batch script, it's a simple batch script which runs all the analysis. And Franco, which is written in Python, does all the crunching. Basically, this is the storage one function, and this is the analysis one. It creates the matrices with the features. Then we learn the model, and when we have the models, we can classify the malware. It's simple. So I'm basically using only open source. I'm standing on the shoulders of giants. Basically the classic scientific Python stack. I'm using NumPy, IPython, Pandas, scikit-learn. I'm running the analysis thing in KVM. I mentioned Cuckoo earlier. And basically I use Mongo and Postgre for storage. At the moment, I have 3 classifiers. The first one use only static features. The second one is dynamic, which use some system calls properties, like arguments properties. And the second one is basically a system call graph, which is basically a matrix of all system calls. Basically, the idea is based on one idea with one great scientist. It's called Wolpert. Anybody heard about Wolpert? He wrote about the no free lunch theorem. So he also wrote about the stack generalization. And basically, Marko talked about convolutional networks, deep learning. This is an old school technique from 1992. It basically uses multiple classifiers. It takes their predictions, uses a meta classifier, and gives us the final prediction. So the training data. The training data was derived from a big data set of 50,000 samples. It was stratified by year and by malware type. The malware type was derived by the antivirus Kaspersky. Thanks to Kaspersky. It helped me a lot. So let's benchmark Malio to others. This is my PhD topic, and I can show all the results. Basically, one guy who was working at the Los Alamos laboratory, now is in Cisco, was the best. It was my idol. And I had so much problem with that paper, and it wasted me a lot of time. So finally, he was the best one, but I managed with some transformation of data. It's not about the result. Machine learning in the scientific community, it's all about the results. If you want to have a good classifier, you have to have 99%. Basically, I think it's better to do a good idea that can classify malware and that's creative than to have a 99% result. Because you have to have a resilient classifier at the end. So some of the problems of this domain are the following. VM evasion in dynamic analysis. This was a big problem. I patched the cuckoo monitor function. Anyone look at the source of the cuckoo monitor function, guys from Reversing Labs. I patched it a lot, and I have so many problems with that. Basically, the cuckoo monitor, it's not that bad, but malware authors are so creative in escaping sandboxing environments. So they are finding every day new ways to escape sandboxing. Also, this model has to have a human in the loop. Guys from Google, Scully, Scully and colleagues wrote about detection of spam advertisements. And they said without a human, without an analyst in the loop, you cannot detect, basically, the ads, which are malicious. Also, the temporal component. I had so many problems while finding some new ransomwares, putting it in the data set, and with the results were so bad. Basically, new malware drifts your distribution of data and it skews your results. So this is a big problem also. One idea, what I plan to do next is to build a phylogenetics tree of malwares. Basically, you have one branch like you saw on the Romanian CERT picture. You have one tree with all malware samples and ancestors and stuff like that. So, future of Malio. I plan to support more formats for it, use disassembly and build another classifier which uses disassembly, provision it to the cloud, and change Postgre with some other technologies like ClickHouse is a Yandex database, column-oriented, I think. Spark, Dask. Basically, I'm benchmarking this together to see which suits more for my usage. This is my talk, so fast questions if somebody wants to ask me on, or you can ask me any questions on my email. Anyone? Yeah, you can basically, this is why I call it framework. You can extend the framework with any classifier you want. You build a symbolic execution classifier, and then you incorporate in the framework. The only problem is you cannot have many classifiers. When you go to 5 classifiers, there's a problem because you have to manage all that. That's the only problem. but it's one idea, not the symbolic execution one, but the dynamic instrumentation with pin and stuff like that. Yeah. Other questions? Okay. Thank you.